Hello everybody, today easy calculus. We learned vector calculus, so it's time to dump Newton's gravity and use field theory. Okay, so what's the difference? I explain here. If you like this video, please do not forget to click like and register. Okay, so this is like advanced high school levels. We talk about calculus and physics, why calculus became important. Mostly it's demanded by physics, particularly vector calculus. So Newton, who invented the calculus? They say Newton and Leibniz. Leibniz is a mathematician, is a genius mathematician. He created calculus from the mathematics viewpoint. The Newton is more precisely the user of calculus. Calculus wasn't used for any other applications. The concept of calculus existed at that time, but Newton is the first one used for analyzing planet movement, and use the planet movement to predict there is a attractive force acting on every mass. So the gravity force is a gravity constant, and the mass to mass and r square. So this is one of Newton's law. Another one is F equals ma, and a is second derivative of distance, right? So here calculus come in, and using this calculus, the acceleration, planet movement is circular, so this movement and this force came from this calculation. This mass is moving around the large mass. The planet movement, plenty of data was available by Copernicus, Galileo, those previous giants. Newton called them giant, and he said in his book, I was on the shoulder of giant to look out, look far away and see what's in there. And he used the calculus to calculate the existence of force, and that was gravity. So this gravity, if you take Earth and r square, and Earth's radius is about 8,000 miles. So on the Earth, this becomes g, gravity constant, g m, or you can write mg, and this g is like 9.8 meter per second square. G is constant. You know why it's constant? Because this 8,000 miles, and you're talking about, apple dropping from tree. The apple is like 30 meters. So G here and here, it's almost same. So we consider as a constant, the constant values on the surface of the Earth. Okay, so this is the Newton's finding. Now the question is, Newton couldn't answer when somebody asked. You have m and m. They are attracting each other. Strange. If there is a moon here behind, it's still attracting you cannot hide. So gravity force is every m in the universe, in the Jupiter here and Uranus here, everything acting. What the hell is this? What kind of force is this? It is very mysterious. Every gravity are attracted to each other, right? And this is the gravity Newton's finding called point to point force. And Newton said, I don't know, that seemed to be the case. Okay, so that was a mystery force. Gravity is every mass attract each other. It's point to point, and you cannot hide it. There's no place in the universe you can get away from this gravity effect. Okay, if you have something, the shield or wall, it still act on this gravity together with gravity on this wall if this wall has a mass. Okay, so this was the early physics, right? So physics, it said it's a point to point, but it changed when electromagnetic force is studied. Like Coulomb, you have plus charge and negative charge, then it's attract each other. It looks like gravity, but electromagnetic field was not following Newton's method. It's invented the new theory called field theory. What the field theory is, if you have a Coulomb here, then it's generate electrical field. If it's magnetic, there is the magnetic field generated, and they are independent, and this relationship is described by Maxwell's. There are 4 equations, and it's match up pretty well. It's predict pretty much all the electromagnetic radiation theory. Like you have an antenna and you receive antenna, and all the communication technology is based on this. Okay, so Coulomb theory is just like point to point, right? But the electromagnetic material, the theory evolved using field theory. It's far more complicated than just point to point. There's no way you can always deal with charge and magnetic element. Okay, so what's happened is we have something called electrical field or magnetic field. What's field? Okay, this is another mystery, and we go back to Newton and say gravity field. Okay, so it's matched up very well. Only difference is the electrical field, we have a plus and negative charge. The plus charge repel, and we never see gravity repelling force because every mass attract. So there is some difference, but pretty much gravity theory Newton discovered can be described as field, right? Okay, gravity field exists, and the gravity field, Newton's force is m gravity field. What is this gravity field? Okay, now the electrical field is negative gradient potential field. This potential field, electrical potential, or you can use the vector calculus, this one, right? So the gravity field can be written the same way. This gravity field can be written the same way as potential field. What is this potential field in gravity? It's like when you move apple back to tree from ground. So this height and the force is going to be the total energy work, right? Work, total energy. You talk about this, the amount of work, this potential energy versus kinetic energy. Remember, is mv square, right? This kinetic energy versus potential energy, h times f. Okay, so this potential field, this is a potential that we calculate the potential only for this distance, but actually you have Earth and you have a potential field going, or I mean sun, and Earth is here. So we calculate this potential field. The potential field is going to be gravity constant, and sun's weight r negative. That's gonna be the potential, the gravity field. This is one direction, I, right? Okay, so this is not r square, it's r, and if you take this one, negative I'm sorry, this is potential, gravity potential. The this is not kinetic energy, it's work energy. It's calculated from sun all the way to Earth. It's, you have to take a derivative to find out the force. Potential gravity potential field, and if you multiply m, that's gonna be the force. Okay, so it's exactly the same thing, only difference is m is positive number but attractive force, and in order to be attractive force for plus charge, it has to be negative charge in the electrical field. That's the only difference. So sign is not same because m is positive, but still it should be attractive force for symmetric consideration, but it's attractive force, it's repelling force, because m, both are m positive mass. So for electrical field, the same charge is going to repel, but gravity field, they attract. So that's the only difference. The difference is only the sign. Okay, so you can tell the field theory can be used for describing the gravity potential and the gravity field. And what's the difference between newtons and the field? Newton is point to point. This mass act on this mass. This mass act on this. But field theory, the mass, sun's weight, the mass create this gravity field, and anything in this field is affected by field theory. So the theory by the gravity effect is going to be pretty much same as the electromagnetic. It's all consistent except for sign, right? So this is the new understanding of the gravity. There must be a gravity field. But actually this is not the latest understanding. Well, Einstein modified this. Gravity field is fine, right? But what is the field? You said the vacuum. Definition of vacuum is nothing there. There's something. The field. The field is in the vacuum. We know the field in the vacuum because gravity work across the vacuum space, and electrical force, magnetic force, act in the vacuum too. So what is, when you say vacuum, the definition of vacuum is nothing. There are a lot of things: electrical field, gravity field, magnetic field. Who knows what else? The field. Okay, so vacuum has a lot of stuff. So the definition of space became a big question in the physics, right? Because field theory sounds cool, using gradient and vector calculus. That's cool, but we still don't know what the field is. Is it just a theory or actually existing in a space? If existing in a space, that means vacuum. There's no such a thing as nothing in the vacuum. There's a something. Electrical field, magnetic field, and the gravity field. Now, Einstein had the idea, special relativity theory. According to this, space sometimes stretch or shrink, and space is related to time, and space is the same 1 inch. Let's use centimeter, more scientific. Here's 1 cent, but this space 1 cent, you try to overlap, then this 1 inch look like this, 1 centimeter. I'm sorry, I keep saying this is a bad habit of using inch. This the American failed to use scientific unit. So depend on location, this 1 centimeter and 1 centimeter, you compare, this looks longer. Okay, this kind of things happen. And field theory get complicated with this kind of special relativity theory. So what Einstein did is incorporated special relativity theory into field theory, create a general relativity, general theory of relativity. Okay, so what he did is, instead of gravity field theory, he said, well, actually space warp around the gravity like this. And when you say, oh, it's warp, so it's another mass come around and fall into this trap, well, that's the image, but actually it's not like that. It's like the space like that, and stretch, 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 here stretch, all the way stretch. So it's not uniform. Space is not uniform. Okay, so when you have here this gradient of space density, so if vacuum has a density, what is it? Okay, still that the basic question of physics, we don't know what space is, but density gradient, okay, is generate gravity field. And instead of a gravity field, Einstein has to make it space itself is like a field. It's warped around the gravity in order to incorporate special relativity theory, because according to this, space sometimes stretch, shrink, and related to time. Okay, so simple field theory of gravity doesn't work. The actually space itself is warped. Okay, so that's Einstein's general relativity theory. Okay, now using this, there are some interesting things came out, like if space warped, then electrical field can generate magnetic field. So there is interesting fact is electrical field and magnetic field actually it's the same thing. It's the same coin. You are looking at from different side. Okay, so but that still doesn't explain the gravity side. Gravity side is different, and that's what Einstein's lifetime work. He tried to combine all of them together, but wasn't successful so far. Physics, nobody can combine them together. So right now, what it stands is general theory of relativity for gravity, and electromagnetic field theory by Maxwell. And Maxwell theory is a little bit more deep understanding is electrical field, magnetic field is same thing. It's just you are looking at the same coin from both sides, so it's just single field, right? And they are field, they are not warped space or anything. Okay, so that's a progress of physics, but a bunch of the vectors, if you get more complicated, it's become tensor, and tensor is used for Einstein's general theory of relativity. So it's a progressing. I hope this story interests you. This overall picture of what's going on in the physics with vector calculus. Okay? We'll see you next video.